So let's work a few examples. The first example of graphing a cubic function, we'll work the easiest example we have, which is f of x equals x cubed. Let's go ahead and draw our graph. Okay, so that's x, that's y. Now, many of you probably already know how that's going to look in the end, but let's use math to tell us what it's going to look like. So we're going to find the first derivative, which equals 3x squared. Then the second derivative, which equals 6x. Now, if you notice that the second derivative equaling 6x means that the concavity is going to be different depending on x. When x is positive, this function is concave up. When x is negative, this function is concave down. Okay? Now, do we have slopes that change? In other words, do we have a max or min max and min involved in this function? In other words, does this function, does it look like this where it's nice and smooth, or does it look like this where it's kind of humpy? Okay, in this case we would have one max and one min, but you see right here in the center, that's where the slope is different than it is here and here. Okay, the slope is positive here, the slope is positive here, but it's negative here. Do we get that with our first derivative? Do we get that dynamic? No. Why? Because this is x squared. So this slope is telling us that for all x, regardless of whether x is negative or x is positive, for all x, the slope will always be positive. Now, what does that mean? That means this function is going to look like this. Now, the question is, okay, exactly where does that function cross the axes? Okay, and how does that second derivative play a role in finding this critical point, the inflection point? Because we don't have critical points of maxes and mins in this example. We only have the inflection point to worry about. Okay, so if we set f double prime of x equal to 0, well then what do we get? We get x equals 0. Okay, that is the x coordinate of our inflection point. Now, how do we find the y coordinate? We plug that back into f of x, and what do we get? We get f of 0 equals 0. So the y coordinate is also 0. In other words, that is where our inflection point is. Now we go back to the second derivative. When x is positive, the function is concave up. When x is negative, the function is concave down. And there we've just graphed a simple cubic function. Let's dial it up one notch. Let's assume we have f of x equals x cubed plus 1. How do we graph that? Well, we break out our xy graph. We look at the first derivative, which is 3x squared. Okay, we look at the second derivative, which is 6x. Okay, same first and second derivative as last time, so it's going to look like the same function, but here's the difference. Okay, when we set the second derivative equal to 0 to find the inflection point, we get x equals 0, which is the same x coordinate for the inflection point that it was last time. But when we then plug that back into the main function to find the y coordinate, guess what? F of 0 now equals 1 because of that 1 there. In other words, when x is 0, y is 1, and that's our new inflection point. Okay, that is our new inflection point. Now, what does that mean? Well, the dynamic of the concavity is still the same. When x is positive, the function is concave up. When x is negative, the function is concave down. Now, why is this important? Well, because we actually have one more point that we can use to tighten this graph up, so to speak. And that is where f of x equals 0. Okay, that is where y equals 0. So if we set x cubed plus 1 equal to 0, what do we get? We get x cubed equals negative 1, and then x equals negative 1. Okay, so when y equals 0, x equals negative 1, and that is where it crosses the x-axis. Now let's get even more complicated. Let's do f of x equals 2x cubed minus 12x squared plus 30. Let's graph that. Now that looks complicated, but it's just like graphing quadratic functions. There's a step-by-step process, and we evaluate each step for what it's worth. So f prime of x equals 6x squared minus 24x. Okay, that's the first derivative. Now we can see that first derivative, that slope of that function, changes depending on the value of x. Now, why is that important? Because this is telling us right off the bat that we don't have a quadratic function that looks like this. We have a quadratic function that possibly looks like this, okay? In other words, it's going to have a max and a min somewhere in it. Why? Because the slope changes depending on the value of x. What about the second derivative? The second derivative equals 12x minus 24. Once again, the concavity is going to be different depending on the value of x. We can tell that right off the bat, okay? So, question is then, what does this function look like? Well, let's break out our xy graph, okay? Let's first set the second derivative equal to 0, because we know since the concavity changes depending on x, we know there's going to be an inflection point. So we're going to set that equal to 0 in order to find it. So that gives us 12x minus 24 equals 0. 12x equals 24. X equals 2. Okay? So at x equals 2, somewhere out here, is going to be the x-coordinate of the inflection point. What is the y-coordinate? We're going to plug that 2 back into the original function, and we're going to find f of 2, which equals 2 times 2 cubed minus 12 times 2 squared plus 30. Now that equals 2 cubes, 2 times 2 is 4, times 2 is 8, so that equals 16, minus 48 plus 30, and that equals negative 2, okay? So our inflection point is at 2, negative 2. It is right there. Okay, that's our inflection point. What does the rest of the graph look like? Well, we found the inflection point. Now, since we know the slope is going to change depending on the value of x, now we need to find where those maxes and mins are, okay? So we're going to set this equal to 0, the first derivative, just like we did for a quadratic function. So we get 6x squared minus 24x equals 0. Okay? Now we're going to factor out an x. That leaves 6x minus 24 equals 0. So one x coordinate of one max or min, we don't know which one yet, one x coordinate is going to be at 0, is going to be at 0. Okay? What is the y coordinate when x is 0? Well, we look at f of 0. We plug 0 back into here for x, and we get 30. Okay? So that's our x and y coordinate for one of the maxes or mins. The second is going to be, the second x coordinate is going to be 6x minus 24 equals 0. And that's going to be 6x equals 24, x equals 4. Okay? So when x equals 4, what does f of 4 equal? Well, we're going to plug that 4 back into the original function. And for this, I'm going to use my calculator. So I get 2 times 4 cubed minus 12 times 4 squared plus 30. And that gives me negative 34. Okay? So those are the coordinates for one of our maxes or mins. That's the coordinate for the other. Okay? So when x is 0, y is 30, somewhere up here. Let's just say that's 30. Okay? So when x is 0, y is 30. When x is 4, somewhere out here, y is negative 34. Okay, so that would be like right there. Okay, so what does this look like? And again, the scale's off a little bit. I'm not too concerned about that as long as it's pictorially accurate when we get done. So we can already kind of tell what it looks like, right? But let's just go through the whole formalities of it. How do we tell then where we're concave up and concave down? Well, that's going to depend on the value of the second derivative at some x. Now, the easiest place to determine the second derivative when you're trying to graph the function is just to use the max and min if you have one. So at x equals 0, what is f double prime of x? It's negative 24. So the function is concave down at this critical point. Okay? When x is 4, what is f double prime of x? Well, that would be 48 minus 24, so that would be positive. So the function is concave up at this critical point, meaning that this function graphs like this. Okay? And that is the graph of, I probably should have brought this out a little bit more. That is the graph of our complicated, relatively complicated cubic function, okay, with the inflection point being right in the center here. Okay, it's not that hard. We're going to go over a couple other examples of the general quadratic function, and then we'll move into a bunch